Today we'll perform a new experiment, galvanometer. You have heard about this before in 2-3 experiments which I have explained. So a galvanometer is that device which is used to detect the current, also to show the direction of current. So this galvanometer, it's a device but it has some resistance. So we will find out the resistance of the galvanometer in the first half, and then we'll find figure of merit of a galvanometer. So about figure of merit we'll discuss later on. So how to find a resistance? We have a circuit diagram here. We have taken one cell and we have taken in our lab Daniell cell. This is key K1, this is key K2. This resistance box is a high value resistance box, we call it R1. Low value resistance box, we call it R2, and this is our galvanometer. Now what is the experiment to start with? To start with, we will just put off this. We don't want this circuit at all. We are only going to concentrate on this circuit, the first circuit. Current flows like this, it goes back in this direction. So the current flows in the circuit. So once the current flows, there will be a deflection in the galvanometer. We need to put it on, and then before that, putting it on, before that we have to remove some resistance from this resistance box. Now we need to remove high value resistance like 5000 ohms, 6000 ohms. Why? Because galvanometer can manage maximum current up to 1 milliamp. So the whatever current flows in the galvanometer is in microamps, maximum 1 milliamp. So suppose we take high value resistance, then it will manage that current. If we take low value, this pointer may get damaged, and therefore we need to remove in the range of 5000, 6000 ohms and perform the experiment. So what we do is, the current flows like this. Let's see what is once the current flows in this and we get some deflection theta. Now the theta whatever you get should be an even number. So suppose I get deflection 20 say. When I get 20 deflection, now there is a next part coming in the picture, that is this one. So I put on this. When I put on this, I remove some value from here. Now when I remove some value from here, this current which is coming here, it is at this junction, some part of it will come here. Some part of the current will come here. So how much is the current coming here? We have to adjust these resistances in such a way that we get exactly half the deflection of the earlier. Deflection was 20, now we want 10. So we remove some resistance. Suppose for some resistance R2 at about 60 ohms, say 60 ohm, deflection becomes 10 divisions. What is the meaning of this? Meaning is, whatever current was coming here, it is exactly divided into two parts. So the major current, main current, which was 20, now it is divided to half. So 10 parts come here, 10 parts come here. So that's why it is called as half deflection method. Now you can see very well, these two are in parallel. And you all know that when two resistances are equal resistance run parallel, current flowing through is same. I and I. Suppose I is the current comes here, I by 2, I by 2. This follows that this resistance R1 and R2 are equal. So R1 is equal to R2. Because the currents flowing in both the branches is equal. So current flowing in the galvanometer and current flowing in the resistance box is equal. And therefore whatever we get value here what is value removed 60 ohms, that has to be equal to resistance of the galvanometer. So we found the resistance of the galvanometer. Now what we have to do, you look at the observation table. Now we have taken readings in the observation table. We will take the readings in the practical lab and we will find the resistance of the galvanometer. For 5 different values of resistance here, we will get 5 readings, and what we get, every reading, only one constant, that is the resistance of the galvanometer. That's all about the first part of the experiment. Now in the second part of the experiment, we are finding figure of merit of a galvanometer. So what is figure of merit? It is the amount of current required to produce deflection of one division in the scale of the galvanometer. For example, this is my galvanometer. This is the pointer 10, 20, 30, 10, 20, 30. So this is 10 divisions, 20 divisions, 30 divisions, and this is the pointer which is moving. 0, 10, 20, 30. Now, supposing this 10 is again divided into 10 equal parts. 10 equal parts, 10 division, this. So this is 1. Least count is 1 division. Therefore, suppose this pointer comes on the first division. This is my 0 and is the first division. How much current it carries for that 1 division is the figure of merit of the galvanometer. Now we learn about it in detail. So let's start with the actual concept. You all know that current in this current is equal to E upon R1 plus G. Remember, I remove this part now. We don't want this. Now we are focusing only on the first part, this circuit. Okay? EMF E upon total resistance is the current in the circuit. That is my current I. Now, we also know that current in the galvanometer which is flowing is directly proportional to division, that is theta. This implies, this means current is equal to K theta. So what I do is, I write here E upon R plus G is equal to K into theta. I can write it like this. Therefore, K, this K is what? K is called a constant, which is called as figure of merit. So what is K? I just write it here. K is equal to current upon theta. So what is the meaning of that? Current upon theta. Current is in ampere, that is unit, and theta is divisions. So this is the unit. So how will you define it? Amount of current per unit division is figure of merit. Now in this experiment we want to find out what is the figure of merit of this galvanometer. So what I do? I write here K is equal to E upon R plus G into theta. So this is one calculation. E we can find out. It is the EMF of Daniel set with the voltmeter, because we want some reading, even if it is not very accurate, but still we will find a voltmeter reading. E how much it is. R is the resistance in the resistance box, which is R1, which we have taken here, plus G into theta. This is, and theta G we have found out. G we have found out already. So we will substitute all these values and find K. But there is one more beautiful method of finding K. Let's see what it is. It is like this. It's a graphical method. E upon K theta is equal to R1 plus G. I bring K theta here. Now I can write here R1 is equal to E upon K into 1 by theta minus G. Modify it. Minus G. Then, now what you all know that, just simple geometry we will study. This is my Y and this is my X. If the graph shows that it is passing through the origin, straight line passing through the origin, we know that Y is equal to mx. If we take this graph parallel line, parallel to this, it is Y is equal to mx minus c, this one. And this is Y is equal to mx plus c. Now look here. In this experiment, R1 is a variable. So we remove different values of R1 and find out the value of theta in the observation table. So R1 is a variable and theta is a variable. E is a constant for that cell. K is also a constant and G is also a constant. So I can compare this particular equation with Y is equal to mx minus c. Now, x is a variable, m, you can see that this is m, slope of the graph E by K. So now, if I plot a graph of R versus 1 by theta on the x-axis, then I may get the graph like this. And this particular distance, let's see what it is. We have equation R1 is equal to E upon K into 1 by theta minus G. Look at the equation. If I take this particular equation of line y is equal to mx minus c, it is comparable. R1 corresponds to y. E by k corresponds to m. 1 by theta corresponds to x. And g corresponds to galvanometer resistance, that is y-intercept. So we can see very well, we get this graph, and on this graph, if I draw this graph like this, I get this kind of graph. So I get this kind of graph. We need to find the slope. So when I find the slope of this graph, it is E upon K is the slope. And if you see the y-intercept, it is nothing but resistance of the galvanometer. This is nothing but resistance of the galvanometer. So here E upon K is the slope. That means K is equal to E by slope. So K is equal to E upon slope. We can find the EMF of this cell, linear cell, with the help of a voltmeter, and slope here we can find out, and we can find a figure of merit. So we can find figure of merit in two different ways. The first part which I have already shown you, and this is the second part. By graph it is very easy to find the figure of merit. I like this method. Now let's say we get the value of this at say 2.0 into 10 raised to minus 5 ampere per division. So what is actually figure of merit? This is my galvanometer, 0 deflection, 10, 20 and 30. Now this 10 is divided into 10 equal parts. So when this is on the first marking, first division, how much current per division? How much current per division is figure of merit? Now 2.0 into 10 raised to minus 5 I can always convert into microamps. So I can write it as 20 into 10 raised to minus 6 ampere per division, or it is equal to 20 microamps per division. What is the meaning of this? When it was one division, the current shown in the galvanometer, current actually which is flowing in the galvanometer is 20 microamps. Now tell me, if this pointer is here, what must be the current in the galvanometer? 30 means maximum current, that is Ig. So that will be equal to 20 into 30, which is equal to 600 microamps for 30 divisions. So you know what is for 10 divisions, 20 divisions, 30 divisions. We know how much current can flow in this galvanometer. This is point 1. Suppose I give you another example. See, I tell you the figure of merit of the given galvanometer is 1.6 into 10 raised to minus 5 ampere per division. So it is 16 microamps per division. 16 microamps for one division. So it will be 16 into 30, that is 480 microamps, full scale deflection. So you can find out how much is the current flowing in the given galvanometer. There is one more term which is called as current sensitivity, and it is nothing but reciprocal. Current sensitivity is reciprocal of figure of merit. So what must be the formula for that? Theta upon I. So what is the meaning of that? Amount of deflection per unit current is the current sensitivity. So these are the two terms we will come across in our theory part, and we may get some problems in future to solve. So this is the part 1, that is the concept part of the figure of merit. In the second part, we will be doing actual experiment, and we will find out figure of merit and resistance of the galvanometer. So you need to click the link in the description box for part 2 and perform the experiment after that. See you once again for the next session. Thank you very much.